hold his feet to the fire and say, well, prove to me it works, Paul, and that I should spend my money on the product. But, you know, any of these things, I mean, take the kids out mushrooming in the spring, and it's always nice, and we got a couple young ones in the room, but not very many. And that's really, that's the group I want to get to, because ultimately they're gonna go through school and they're gonna ask the teacher, how come you don't teach us about fungi? We should be learning about fungi, and things like that. And all of these things from European books.
Yeah.
Europeans and kids do go out, usually with grandma and grandpa, into the woods and learn to pick the mushrooms. Okay, but even if you don't care about any of those sorts of things, you know, that you need to have an appreciation for that these things are important. Has anybody been to the Desert Museum in Tucson? Oh. So my wife and I were down there visiting some friends, and they took us up to the museum, and they had this display that was a little bit of soil blown up 1,000,000 times, and then with all the different things in the soil labeled, and the descriptive stuff, I'm reading, and then I come upon this thing that says, no fungi, no plants, no animals. And I said, wow, that's great, you know, so in addition to the Greg Marley quote, and you know, I add another thing to my stable of quotes that I need to remember. So this is out of some college textbook or another, basically a simplified representation of an ecosystem. So here you have the producers, the green plants. They get energy from the sun, carbon dioxide from the atmosphere, water, nutrients of different sorts from the soil, and the plants can make everything they need once they have those raw materials. They're wonderful biochemists. And those plants then are the base for the food chain for everything else. So the bunny rabbit comes along, it's eating the grass, you know, the fox comes along, eats the bunny rabbit, and so on and so forth, the food chain, but it all starts with the green plant. But keep in mind, you know, the leaves die and fall off, roots die back. You've got a little arrow coming in on the back end of the bunny that they don't label. All of that stuff needs to get back to atomic or molecular form so it can be used by a new generations of organisms. And if you've taken any biology in school, you know, you spend about 5 minutes, maybe 10 on the fungi, and they say, well, if it weren't for the fungi, we would all be buried by all these leaves and twigs and everything, and so forth. So it's very true, but there's a part that they're not taking into consideration when they tell you that. So what are the different roles of fungi in those systems? So the one you always hear about, the decomposers are the saprotrophs. Sapro means dead, troph means feeding, so you're feeding on dead material. So all the ones in the display where you go around the side of the table where it shows the ones that are growing on wood, and those are a real obvious example of things that are decomposing things. Symbionts, symbiosis just means living together intimately. Okay, sometimes that's a parasitic relationship, sometimes it's a mutualistic or a beneficial one. There are certain fungi that are predators, and mutualistic symbionts. And then for most fungi, we're not exactly sure what the heck they're doing. So what are some of these ones that we're not really sure? If you go out and it's probably true of oak leaves if you went out here to any live oak tree, but if you come up to where I live in Washington, you go to a Douglas fir tree, and I have no clue how many needles might be on an individual tree. But every single one of those needles will have a community of fungi living in it. And we don't know what the heck they're doing there. And practically every needle will have a slightly different community than all the other needles. So two ideas about what's going on there. One is that, well, these are fungi that are just first in line at the buffet table. And when the needles die and fall off, they're there to get to the sources. The other one is that these fungi, could be producing chemicals that deter, insects and things that would want to come and eat the needles. And, if you've got every single needle having slightly different chemistry, then yeah, an insect may be able to eat this one, but it might not be able to eat the next door one. So it could be that, it's anti-herbivore sort of a mechanism. Well, we don't know. Soil fungi. A lot of you know about all the DNA research people are doing, and the technology is proceeding really rapidly. And so, if you wanted to study the fungi on roots, for instance, you'd have to extract those roots from the soil, get some of the fungus off of there, and then run it in and do the DNA analysis. Nowadays, you can take a soil sample and run the soil sample through, and they get these printouts with, well, we got 3,482 different reads. And those are just different DNA sequences out of the soil. And they can say, okay, we've got 500 different fungi down there. We don't know what any of them are or what any of them are doing, but they can do this sort of stuff now. So that's really increasing our ability to say, holy cow, how many fungi are there in the world? And will we ever really know what most of them are doing? And then there are a number of fungi that associate with animals. So animals like cows, that rumen and so forth, they eat plant material. They're not really digesting it. They've got microorganisms in their gut. And the microorganisms are doing the digestion for them. And some of those microorganisms are fungi. Same thing with termites. Termites can't digest wood on their own. It's the microbes in their system that do it. There's a group of fungi called the Labiobeniales. Very simple, reduced little things. They just amount to a few cells. And you only find, particular species, you may only find it on the left shoulder blade of the female of the species of insect. So that's specific. And nobody knows what in the world we're really doing there. So still lots to learn. Saprotroph's a little bit easier. We've got a sulfur shelf, or some people call it chicken of the woods. I like sulfur shelf better. Rotting the hemlock log. Use a little Marasmiellus on a twig, Strobilurus on a Douglas fir cone. And here's a Gymnopus or Philidea. You can see the mycelium here that all those microscopic hyphae have aggregated in so that now it's the thickness that you can actually see. So it's kind of like an individual human hair. You might not be able to see very well, but you can see a ponytail or a pigtail, something like that. So lots of saprotrophs. And ecologically, they can be very important in addition to their recycling function. And here's a conch of some sort, a polypore, wood decomposer. These things soften the wood, and so things like bark beetles can come in and soften it more, and soften the wood such that a woodpecker can come and make a hollow for the nest cavity. And then when the woodpecker leaves, then other birds can go in and use it and so forth. So these things have ecological roles beyond just the recycling stuff. There aren't, there's quite a few. Among the mushrooms, there aren't a lot of parasitic fungi. Most of the plant parasites and dangerous things are all microscopic fungi that people work with. But here's a honey mushroom. Lots of honey mushrooms growing on a stump of a tree. They can be very good decomposers, but they're also involved. It's a root rot fungus, and it was probably instrumental in this tree dying in the first place, and then it is able to decompose it. These form these thick black cords, rhizomorphs, and then they can travel over to another root system of another tree very easily. The honey mushrooms are the ones when you see in the news about the humongous fungus. The original one was in Michigan, and now the record holder is in northeastern Oregon. You might have seen the U-Haul truck, and they had a different thing on the side for each state. So the Michigan one was a picture of a mushroom, a picture from Tom Bolt. They decided they didn't like this dull color, so they made the mushroom purple. And here's an earth ball, a scleroderma with a species of Boletus, and nowadays Parasitica boletus that's on it. Here's a cordyceps on a, I guess that's a pupa or something, some life stage of an insect. So, well, fungi are able to parasitize a lot of other organisms. And again, here it's it can have an important ecosystem role. This is laminated root rot, Pholinus weiryi, and maybe it's not in Pholinus anymore. I'll have to look. But a group of students looking at some dead trees. So these are Douglas fir trees. The green trees around it are hemlocks. And hemlocks aren't nearly as susceptible to this as Douglas fir is. But what this does is it creates a gap in the forest. And now it lets more light in. The hemlocks and things that are down lower and the herbaceous plants and stuff now get more light, and so now they can grow. And this sequential process of gap formation stuff is what leads to the classic Pacific Northwest old growth forest. That old growth isn't just all uniform old trees, it's a whole mix of very old trees, very young trees, big trees, little trees, so forth like that. And then there's predators. Most of these are fungi that rot wood. Wood is not very high in nitrogen, and nitrogen is something that all organisms need for making proteins and so forth. So the thought is that these predators, it's the nitrogen that's driving things. But this one, these are the lethal lollipops. So basically just little side branches off of the hypha here, and they're sticky. And so this little nematode worm, nematodes, some of them are microscopic, some of them are a little bit bigger than that. They can be important in your garden. There's pathogens on the roots of your plants and things like that. But a lot of them are probably not doing much of anything down there. The nematode gets stuck, held in place, the fungus grows into the body of the worm and mines the nutrients. This one makes little lassos that it's a ring, usually with 3 cells, and when it kind of tickles the inside of the cell, it triggers the inrush of water, it expands the cells, and gotcha. It's the same sort of a mechanism, those Venus flytraps that allow, lets the leaves of the Venus flytrap flow. So some of the, most of the stuff is microscopic, but some of them are a bit bigger. And you do need to watch out. You're out in the forest. Drew Parker used to send these things out every Halloween. He hasn't done one in a while. Okay, so then the mutualistic symbionts. Many of you know about lichens. So lichen is a fungus with a green alga or cyanobacterium, or both of the others. The alga with cyanobacterium do photosynthesis to provide food, and the fungus provides nutrients and basically forms most of the body of the organism. Some of you may have heard that, oh, we need to rewrite all the textbooks about lichens because they've now found that there are some Basidiomycete yeasts that seem to be regularly appearing in lichens. And I go, well, let's hold off rewriting the textbooks until they find out if those Basidiomycete yeasts are actually doing something important in that. It could be, or maybe not. And talked about the animal guts, and then mycorrhizas. And this is the stuff that I go about. Again, myco is fungus, rhiza is root. And basically, it's a fungus that's in close relationship with the roots of the tree, and in this case, it's a mutualistic one, so they're both benefiting from this. So, if you go to Sweden and you find a Scots pine tree, and look at the root system, you'll see that the roots get finer and finer and finer, and eventually you get out to the finest tips of the roots, and you'll see that they're all coated with the mycelium fungus. And then the mycelium then extends out into the soil, and for certain of those species, things that can produce mushrooms, mycelium will produce mushrooms. What are they doing? Well, the fungus is down there getting nitrogen, water, and phosphorus and other things out of the soil and providing them to the plant. And the plant is doing photosynthesis and producing sugars, and it's giving sugar to the fungus. Okay? So that's the mutualistic relationship. They're both benefiting from the other. And bottom line is, none of our forest trees would be out there if it weren't for these fungi. And that's true of most of our plants in general. There are some plants that are fairly relatively more recently evolved that appear to be able to do without any sort of mycorrhizal fungi. But most plants need them to live. You put them in your garden, you provide the fertilizer, you provide the water, da, 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 da. Okay, so the original studies that were done on these things, there were a lot of this big plant, little plant stuff. So they were able to probably use some sort of a fungus killer in the soil here and not here. Plant the same kind of, you got corn on either side and whatever these other things are, onions or something. And you can see that the plot without the fungi, the plants are smaller, and in some cases they didn't even grow. So there was that first level of understanding that, okay, plant plus mycorrhizal fungus, plant goes better. And it's easy to see why. This is a little, everybody know what an ant farm is? Plexiglass box, and you put sand in, you put the ants in, and then you watch them, building their tunnels and things like that. So essentially that's what this is. That's a dwarf birch. Put some soil in there and add a fungus to it, and there's a root, root. All this other stuff, that's fungus. That's the mycelium of the fungus. So 100 to 500 kilometers, that's 60 to 300 miles of hyphae. A kilogram of soil, and a kilogram is 2.2 pounds, so imagine kind of like half a bag of sugar. 300 miles of hyphae going through that thing. Provides lots and lots of absorptive area and so forth. And so it's easy to see why the plant might benefit from this. Because these hyphae are much, much smaller than even the smallest root hair. They can do a much more efficient job of absorbing stuff, and many of the fungi actually do have processes by which they actively make minerals, nitrogen, phosphorus, and so forth available. Okay, so the main take-home lessons about these things, when the quiz comes at the end of the hour, there's lots of different kinds of mycorrhizas, different groups of fungi, different groups of plants, and so forth. It's not just one sort of thing. In terrestrial habitats and even places like salt marshes and stuff, they're always there, and nearly all the plants have them. The main exceptions tend to be weeds. So, all the mustard on the hillside there, and the road cuts and things, mustard is one of the sorts of plants that typically isn't mycorrhizal. But, any of your oaks and grasses and things in the typical environment is all wrong. They've been around since the get-go, as far as plants coming on the land, and without them, we wouldn't have all these green plants that we have. So, different types, ectomycorrhizas are the ones that I'm most interested in, both because of the fungi that are involved, as well as the plants that are involved. So, non-mycorrhizal root, mycorrhizal root, you can see when you've got a mycorrhizal form. So this one's on a pine, that one's on a pine. You can tell because they make these nice little wishbone branch dichotomous branch mycorrhizas. For some reason, pines do that and nothing else does. So this is some other species of tree that you can see that, you know, the fungus coats the thing, and then they'll, maybe not in the back, but you can see the hyphae that would be going off into the soil. Ectomycorrhizal plants, the pines, all of the things in the pine family: pine, spruce, larch, hemlock, Douglas fir, all of these things. So a lot of the forests up where I live, and here's Yosemite Valley, and Yosemite has a lot of ectomycorrhizal trees, Sierra Nevada, and so forth. And a lot of the fungi that provide, produce ectomycorrhizas are big fleshy mushrooms, including things like golden champurels, Boletus. This one was actually Boletus rubriceps. We used to call it Boletus edulis, but it's somewhat different. This is the big Rocky Mountain, very popular edible woolly rusculas. Not much as far as edibility goes, but they're very pretty, and they're a big part of most forests. And then the dyers, the wool dyers and things, these Germosity, group of Cortinarius, bright red gills. These are things that produce, you can get nice red colors and so forth. Not easy to get red with natural dyes, to demonstrate. So, basically, again, the interest in understanding global warming. You hear a lot about carbon footprints and carbon sequestration and carbon banking and things like that. Most all of these sorts of things, they pay almost no attention to anything going on below ground. And so, I always keep a grain of salt for any of these modeling results, because I go, well, you guys aren't paying any attention to what's going on right now. So here's another of these ant farm things, and they take carbon dioxide, in which all the carbon is the radioactive form, carbon-14. So you've got the right kind of fancy lab equipment, you can make images like this, and it shows after some chase period, which I don't know what the chase period here was, but you dose it, and then you wait a while, and then you put it in your imaging machine, and here's where most of the carbon is, all out there in the active growing zone of the fungus. So things like that, the climate modelers and things aren't paying any attention to. And is that important? Well, a group in Sweden did an experiment. They went out to a Scots pine forest, and it was already scheduled to be logged, so they didn't unnecessarily kill a lot of trees. But they went out, and in the test plots, they girdled all the trees. So if you strip basically the bark from all the way around the tree, you cut off the nutrient supply down to the root system, and when you do that, the trees die. Okay, so basically they stopped that flow of carbon down into the mycelium and so forth. And then they had other plots where they didn't do anything. So the way you generally gauge the level of biological activity in soils is you measure the amount of carbon dioxide coming up off the soil surface. So when we're breathing and so forth, we're exhaling carbon dioxide. So are all these other organisms down there. So if there's more activity, more carbon dioxide, we take PVC, large diameter PVC pipes with a lid on it, basically, and a little port that they can stick a syringe or something in and sample the gas. They leave it there for a period of time, take that gas back and analyze it for the percentage of carbon dioxide. And the plots where they girdled the trees, the carbon dioxide was less than half of what it was in the control plots. So, showing that flow of sugar down into the mycelium, and some of that is going to get out into the soil and be used by other organisms and so forth. So, that flow was really important in terms of the activity overall in the soil. And they also looked at mushroom production. So, in the plots where they girdled the trees, I think in each plot there were something like a dozen mycorrhizal mushrooms belonging to a total of 4 different species in all the plots. versus an average of 200 and some mycorrhizal mushrooms in control plots belonging to 15, 20 species or something like that. So for those of you who are out hunting mushrooms and wondering, is it a good year or bad year or whatever, all depends, a lot of it depends on how good a year the trees were having. So you can't just rely on, oh, it's raining, there's gonna be mushrooms. Because if it's been dry, and the trees haven't been doing well, they haven't produced a lot of sugar for fungi. Fungi don't have a lot of sugar in their bank account, and they're not gonna be able to make mushrooms. So it's all of that stuff is related. Another of these mushroom or ant farm things, the artist added the blue sky and clouds. What they did was they planted a pine seedling, and then a couple of weeks later they came along and planted 2 more pine seedlings of a different species of pine. One of them is Scots pine, the other is lodgepole pine, and I can't remember which is which. But, so again, you got some roots, got a lot of mycelium, but what is mycelium? And now that connects to the roots here. And roots and connects. So there's potential there for these 3, maybe someday trees, to be tied together in a network where they could move material from one to the other. And that was Suzanne Simard, who's at the University of British Columbia now. And that was she did her PhD research on this issue and got on the cover of Nature, which is a very prestigious science journal, and for a grad student to get on the cover is really a big deal. Science News picked it up. Communism and trees rotating around. So the notion runs counter to a lot of traditional plant ecologist thinking, where everything is viewed in terms of competition. So you go, well, might there be something else going on besides competition out there? And so if you imagine you're looking down on a forest, and each of these spider things is a tree with its main roots going out, and each of these different patterns is a different fungus mycelium, you can see that each tree can be associated with lots of different fungi, each fungus can be associated with multiple trees, and that opens up all sorts of possible ways that things could move. Really, really, really hard thing to demonstrate in a mature forest in the field. But the one group of plants that we absolutely know what's going on is with these Indian pipe, coral root orchid, snow plant. These are plants. They're not green, so they can't make their own food. They can't do photosynthesis. Where do they get their food? If you look in wildflower books, they'll tell you they're saprophytes, and their root systems are breaking down leaf material and so forth. And that's BS. Plants can't do that. They're associated with fungi. So if you look at the root system, the root systems are definitely not designed for absorbing. So remember that fungal mycelium is designed for absorbing lots of little fine branches and things. Little stubby, thick things are not good structures for creating absorption there. So, long time ago, German scientists realized that all these little tips on these things were covered with fungus material. And you can even follow out here and see some ectomycorrhizal root tips and so forth. So, this is a different plant. This isn't an Indian pipe, but same idea. It's got the root ball down here, and that root ball basically is connected to mycorrhizal fungus, which is then connected to the roots of, in this case, a conifer tree. And the fungus is getting carbon, sugars and things from the tree, which the Indian pipe gets, and it's also taking nutrients up from the soil, which the Indian pipe gets. And is the Indian pipe contributing anything to the party? We don't know. It might be, and it wouldn't surprise me, but if it is, we don't really have any idea what it might be. So, these plants are very good taxonomists. They know which fungi they like to live with. And in this case, I don't know how far south candy stick comes. I guess Mike Matsutake may get down here, but not nearly as much as it does in Northern California and up into Oregon and Washington. But as far as anybody knows, this candy stick plant only grows on the mycelium of Matsutake. So if you're a Matsutake fan, you go out, May, June, July-ish, with your GPS unit, take waypoints wherever you find the candy stick, and then go back in the fall, and that can may give you a leg up on finding Matsutake. Okay, so I think we've just about gotten to the end, not horribly over an hour. But this, again, the main idea is that green plants and things rely on these fungi, and everything we do ultimately goes back to the green plants, food, and so forth and so forth. So the fungi and the plants and animals, so we need to appreciate the fungi. So I'm happy to hang around and answer questions, otherwise class is dismissed.
There's something at 2:30, right?
Yeah, the whole thing goes till 4. We're probably gonna. Lindsay, how much longer did you want to stay? Did you want to